doing is writing different transformed versions of these functions. So on this linear function, we're going to write this transformed equation, y equals 2x plus 3. Now, if you're looking at that going, well, then you just graph it as a y-intercept of 3 and then a slope of 2. We can do that, but we're just going to practice applying the transformation rules to it and interpreting what these numbers mean transformation-wise. All right, folks, what's that plus 3 on the outside doing? Up 3. So remember, outside numbers, positives go up, negatives go down. I think of my arm because it's more outside my body than my eyeballs are, which is the inside transformation. So plus 3 on the outside is going to move us up 3. Now the 2 is getting multiplied out in front. So outside numbers affect our y values. So this is going to be a vertical, anyone remember? Stretch. Vertical stretch by 2. So that is how we describe the transformations. Now to actually do the transformations and apply them to our parent table to get a new table, we need to turn these transformations into algebraic transformations by deciding which of these are going to affect my x values and which ones are going to affect my y values. If I vertically stretch the graph, am I affecting in the x direction or y direction? The y direction, y-axis. And if I slide it up 3, that's affecting my y values as well. So my x values, nothing's affecting them. They're just going to skedaddle straight down from the parent table and stay the same. -1, 0, and 1. Now, the y values are going to be vertically stretched by 2 and then up 3. How we do the transformations is basically how they appear in the equation. The 2 is multiplying, so I'm going to do 2 times the y values and then add 3. So it's times 2 in the equation, it's plus 3 in the equation. So we're going to take the y values times 2 and add 3. So following my order of operations, 2 times -1 is -2, plus 3 is 1. If you are not so great with integer rules, please use your calculator to check yourselves. 2 times 0 is 0, plus 3 is 3. 2 times 1 is 2, plus 3 is 5. And if we plot those points, backwards 1, up 1, 0, 1, 2, 3, and then 1, 1, 2, 3, 4, 5. Swoosh. And that is our transform graph. And does it look okay, Coolio, with how we would graph a line normally? Yep, y-intercept of 3, there it is, up 2 over 1 for our slope. Now, if you're looking at that going, wait, isn't it supposed to be like symmetrical? Folks, that is for inverse functions, not transformed functions. This is just a transformed version of my parent function. It is not the mathematical inverse of it. So that's something that sometimes students will get confused in this chapter. When I say inverse, what should you think? Switching the x and the y values around. So inverses are opposites. We're switching x and y. This, I'm not finding the inverse. I am just straight up transforming the function in some way. Now, if I asked you to find the domain and range of that pink line, what would it be still? All real numbers. So I'm going to draw a box around those in pink because the domain and range stay the same. All real numbers, all real numbers. Transforming it isn't going to affect it for our linear functions. For the absolute value function, let's go ahead and write it up here. Y equals negative absolute value of x plus 2 minus 3. So I normally start with the right side transformations just because I think they're a little bit easier. What's that minus 3 on the outside doing? Down 3. So on the outside, consistent with the signs. Up 3, plus 3, down 3, minus 3. Now for this one. A +2 on the inside, so shift the eyes left and right, but we cross them because it is the opposite of what we would expect with the sign. Oh, that's a headache. Is that going to move us left or right? Positives normally go left, but it does the opposite of what we, positives normally go right, but it does the opposite of what we would think. So that +2 is going to move us left 2. Does anybody remember what a negative being multiplied on the outside does? That is a vertical reflection. So folks, which of these transformations is affecting my x values? Just the left 2. But here's the tricky part, and I would probably highlight this. It is x +2 in the equation, but in our algebraic transformation, we are going to subtract 2 to actually move those points to the left. So we're crossing our eyes to figure out the transformation direction, and then we're basically crossing our eyes again and doing the opposite sign when we actually move the points. Folks, here's the deal. You guys did awesome with describing transformations when we were doing those flashcards and everything. You guys are on that. That part of the homework quiz went fine. However, this graphing part, not so much. So what I'm going to encourage you to do, especially if you're worried about goofing this thing with the sign, after you transform your table and make your graph, check and see if it makes sense with your descriptions. If there doesn't seem to be a match, or if you're like, it seems like my graph has moved right 2 instead of left 2, that probably means you goofed the actual algebraic transformation. So x +2 in the equation, x -2 in the formula. And that is the only place where that happens. Everything else is consistent with the sign. So to vertically reflect my y values, we take the opposite of them. Negative times in the equation, negative times in the transformation formula. Then if I'm moving down 3, we're going to subtract 3. And that's what we're going to do to manipulate our table. Folks, I want you to complete the transform table and draw the graph. -1 - 2, -3. 0 - 2, -2. 1 - 2 is -1. For the y's, the opposite of 1 is -1 - 3, -4. Opposite of 0 is 0, -3 is -3. Opposite of 1 is -1, -3 is -4 again. So plotting those points, backward 3, down 1, 2, 3, 4. Backwards 2, down 1, 2, 3. Backwards 1, down 1, 2, 3, 4. There's our transform absolute value. So to check this, does it look like it has been vertically reflected and flipped upside down? Yup. Does it look like we have moved it left 2 and down 3? Yes. So if our graph was over here and we were doing our check, we'd be like, oh, it's going right 3 and down 3. That probably means I did the opposite sign with the x. So again, once you're done graphing it, make sure it matches those visual transformations. So what about the domain and range? What's our domain for that pink absolute value function? It is still all real numbers. It's going all the way left and all the way right, so it's all good. But is our range the same? I'm going to draw the range over here. Our range starts at -3 and is covered going down. So y less than or equal to negative 3 or negative infinity to negative 3 with a bracket. Folks, if you are an interval notation person, please put an important box around this because the negative infinity has to come first from the bottom up. So for inequalities, it's always y is less than or equal to something, y is greater than or equal to something. But here, the negative infinity has to come first because it's chronologically less than that. So just be careful if you're using interval notation. Folks, I'm going to go ahead and turn you loose on the next one. The quadratic transformed function I would like you to do is y equals 1/2 x squared plus 2. Start by describing the transformations and manipulate your parent table. You don't have to do that extra point we did 2, 4. That plus 2, is it on the outside or the inside? Outside. So that's going to move us up 2. How do I know it's not on the inside? Because it's not in parentheses getting squared with the x. That 1/2 is going to be a vertical shrink. I started writing stretch shrink. Remember that your fractions are shrink numbers. 1/2, 1/3, 2/3, 3/5. So if it's a fraction between 0 and 1, it is a shrink number. Vertical shrink by 1/2. So I'm vertically shrinking. I'm moving up 2. Are those affecting x or y? They are both affecting y. So to affect y by these, we're going to take 1/2 times the y values. Again, it's a 1/2 times in the equation. It's a 1/2 times in the actual transformation. And then plus 2. And then I make my happy little transform table, bringing down those x values, -1, 0, and 1. And then 1/2 of 1, oh, it's 0.5, plus 2, 2.5. We'll just work those decimals. 1/2 of 0 is 0, plus 2 is 2. And 1/2 of 1 is 0.5, plus 2 is 2.5. So backwards 1 up 2.5, 0, 2. Forward 1 up 2.5, and it looks like we're getting kind of wide as we're going outward. So what do you think? Does it look like we move this graph up 2? Yeah. Now, vertically shrinking it means we're pressing up and down towards the vertex. Does it look like we're squashing that blue parabola? Yep. So shrinking is pushing vertically, stretching is pulling vertically, like a rubber band. So if I vertically shrink it, I'm squashing it, and we should get this wider parabola. Hey, what's our domain for that pink one? It's still all real numbers. But the range for this one would be y greater than or equal to 2 or bracket 2 to infinity. And why is it a bracket, not a parenthesis? Because we're getting that value. It is the vertex. It is a point. That's why it's greater than or equal to. That's why it is a bracket. All right, folks, let's see what you can do at this next one, this cubic one. Y equals -2x cubed. Y equals -2x cubed. Hey, how many transformations is that? That's the real question, isn't it? Negative 2 is one number, but it's 2 transformations. See what you can do. Describing the transformations, making the table. Why did I put that table there? Let's move that table down here. What's that negative doing? Vertical reflection. And what's the 2 doing? Vertical stretch by 2. So what students will sometimes do with this is they will take that negative 2 as a shrink number. Stretch and shrink are always positive. Shrink is positive fractions. Stretch is positive numbers. So as soon as you see a negative, that is automatically a vertical reflection. So how are we going to vertically reflect and stretch by 2? Exactly as it is in the equation. I'm multiplying by negative 2, so I'm going to multiply my y values by negative 2. So being very careful with your signs here. That's what your new table should look like. Backward 1 up 2, 0, 0. Forward 1 down 2, curving up through this point, curving down through that point. Does it look like we have vertically reflected this and flipped it top over bottom? Yep, that piece went down there and that piece went up there. So we have vertically reflected it. What about vertically stretching it? Have we taken that blue one and stretched it vertically? Yep, that quote-unquote slope is different between that central point and this point. We're going up 2 and back 1. So it does look like we have stretched it vertically. So it checks out. What's our domain and range of that transform function? All real numbers for both. Whoop. All right, folks, last one. For the square root, I want you to do y equals the square root of x plus 2 minus 4. Also, folks, something we didn't talk about before you do this one, the shape of the square root is important to know when you are identifying transformations based on the graph. So the square root shape is something you should memorize. It starts at a vertex and is pitched going to the right, curving up. So square root graphs are always doing this. If it curves downward, then you know there's been a vertical reflection. If it's going the other way, well, it shouldn't be going the other way. That arrow should always be going to the right, but it will be going down and to the right if it's been vertically reflected. So, folks, state your transformations and work that transformation table. minus 4 on the outside, down 4. Plus 2 on the inside, left 2. Now it's plus 2 in the equation. It's minus 2 in the algebraic transformation. Y minus 4, exactly as it is in the equation. It's just those inside ones that switch signs. There's what your table should look like. There's our new graph. Does it look like we have moved left 2 and down 4? It sure does. Now our domain and range for this one. The domain values are now starting at -2. So x greater than or equal to -2. Range values are starting at 1, 2, 3, 4. So -4. Y is greater than or equal to -4. If you wanted to use interval notation, bracket -2 infinity and bracket -4 infinity. Square root ones are definitely the toughest because the table is different. The graph only has an arrow on one side, and we're just not as comfortable with square roots, and the domain and range are different. Folks, on all of the other ones, the domain is always all real numbers. These ones have a range of all real numbers. These ones start at 0 to infinity, and actually this one goes from 0 to infinity too. But the square root one is probably the one that you will have to study the most. So folks, hold on to this. I think this is a great resource for you with studying. Are we feeling better about transformations and the parent functions that we did last week? All right.